So formally welcome you all in today's class, and we are here today supposed to see our the next agenda is of discussion is the electrodynamometer type instruments. So under this series of module number one, measuring instruments, um, as in the last lecture, continuation to last lecture, we discussed the moving iron type of instruments, okay, as compared to the PMMC device, PMMC method for the measurement of voltage and current. Yeah. So now today we are going to consider our discussion over the next topic, that is the electrodynamometer, or sometimes it is also known as electrodynamics type instruments. So this is one another class of electromechanical type of indicating instruments. Now, what problem with the other measuring instruments till the time we have discussed, that is primarily PMMC and moving iron type, MI type, that it is required to necessarily calibrate for the AC measurement. So that means whenever you are going for the AC measurement, you are required to calibrate the instrument. Particularly when you talk about AC measurement, you know that we have discussed that why PMMC efficacy is poor, which that can perform around 45% efficiency as compared to the DC. So for the as far as the DC measurement is concerned, of course we will prefer PMMC. But as far as the AC measurement is concerned, we try to go for a replacement, that is the moving iron type of instrument. And under the other moving iron type of instruments, we discuss the both repulsion and attraction type method. But in that case, as far as whenever you go for the AC measurement, the AC calibration of that kind of instruments, that is the moving iron kind of instruments, and as well as even the PMMC instruments, okay, that cannot be correctly done. Okay, why it cannot be correctly done? Because whenever you wanted to calibrate is something, you should have ideally you should prefer a mechanism where the DC supply is there. So using DC supply you can calibrate it. That means you calibrate the pointer, the indicator, okay, the display. That means ultimately the instrument for the measurement purpose. And once the device is calibrated for that particular frequency as far as the AC measurement is concerned, in that case you should transfer the DC. You should remove the connection of the DC supply, provide the AC supply, and still the instrument should perform with the same amount of accuracy. Okay. So this cannot be correctly done as far as the moving iron type of instruments are concerned. Okay, because it requires a transfer type of property which is not there. Or in other words, you can say a transfer instrument is one that can be calibrated using a DC source and then can be used without any modification in that instrument for the purpose of AC measurement. Clear? So it requires that kind of property. It means what? It means what is DC? Basically, fundamentally free from the frequency. Or you can say that the frequency is very, very low. Okay? For low frequency range, I would say, if it is not perfect DC. Here. So if frequency is tending to zero, so that means your time period is tending to infinite. So that means it is as good as you are trying to stretch a signal to the up to certain extent during the operation, that you can say that it has a consistent amplitude and which is free from the frequency. That is something nothing but it is a DC characteristic of a signal. Now this requires the transfer type of instrument. Okay, so that may have should have a same amount of accuracy as far as the both AC and DC class are concerned. So today we are going to see in next couple of minutes that electrodynamometer is an instrument that can provide you that kind of feature. Got it? Okay. Now keep it separate at one way. Now consider a standard. Clear? Because what is the primary standard? If you will even uh, go through the reference materials, good standard books, you see, so for example, we have discussed the Western standards cell, okay, which is nothing but it is a DC cell. Now, I have been told you that as far as the India is concerned, these facilities are located at a very specific place. Okay, for example, National Physical Laboratory, which comes under the CSIR, Delhi, New Delhi. Okay, now you cannot shift these kind of instruments readily everywhere during the field measurement for the precision calibration purpose. Okay, so these standards, when you talk about the standards, these are the precision registers and the DC cell. So it is obviously, therefore it would be impossible to calibrate an AC instrument directly against the fundamental primary standards. Okay, primarily we call these primary standards. And what is PMMC? When we use it calibration purpose, I have been number of time, okay, pronounce that particular terminology, that is we call secondary standards. Okay, may not be perfect as primary, but it is more than enough to calibrate a device for the accurate measurement of a good high resolution measurement of the field instruments are concerned, as far as the field instruments and field instrumentation are concerned. So the calibration of an AC instrument, how will you perform? So first, you use a transfer instrument which is being calibrated on DC. Then this calibration is then transferred to the AC instrument, all the using alternating current, okay, at that given operating condition, okay. And in this case, electrodynamic instruments are generally capable to provide these kind of services. So today what we are going to see, the electrodynamometer or electrodynamics type of instrument is also called as a transfer type instrument. Okay, be noted this. Clear? Now when you see the circuit diagram of an electrodynamometer type instrument, it looks like this. So primarily you see that it is entirely is a series connections. Okay, so there are the two coil of the equal number of windings, which is divided under a keeping a moving coil. So the two side coils you see, these are considered as a two fixed coils. So let us, I am assuming L1, L2, where the number of windings are same. So that means theoretically both will produce the same amount of inductances. So ideal condition, you can say L1 is equal to L2. Practically, no two devices can be exactly same. So even for the precise measurement, I am assuming that it is L1 is equal to L2. Whereas there is a spindle, there is a pointer which is attached through a spindle, and this part of the coil is actually movable, so it is acting as a movable coil. Clear? Okay, so these movable coil are attached through this particular pointer, and then thereafter current is exit. So that's how the circuit is complete. Clear? So because of this case, you can see that as far as these electrodynamometer type of instruments are concerned, it offers the measurement of voltage and current. This measurement of voltage, uh, it can measure AC voltage and AC current at the various wide range of frequencies, even from the low frequency range to audio frequency. That means typically very high frequency. Audio frequency range is something around between um, roughly around, you can say that 0 to 20 kilohertz. Clear? Or you can say that it is roughly around 0.3 to 15 kilohertz on an average. Clear? So they are used, they can be, that can be used as a wattmeter, voltmeter. Okay, even with little modification you can use it for the power factor measurement also, the frequency measurement also, and so on. Yeah. Now, as you know that I've been already told you in the beginning that these all the class device are the current sensitive device. So electrodynamometer is also not indifferent. It is also a current sensitive device. Yeah. Now, as far as the range is concerned, it can offer you the measurement up to the range of around hundreds of milliamps as far as the direct measurement are concerned. Obviously, which is much more as compared to the de-arsonable meters, that means the PMMC meters, because PMMC meter range starts from the microamperes, okay, tens of microamperes to hundred of milliampere. And here it can also offer you a little bit around hundred of milliampere. Yeah. As compared to PMMC device and the moving iron type of device instrument method, Electrodynamometer have little low sensitivities. Okay, so the sensitivity is varying from roughly around 20 to 100 ohm per volt. The sensitivity is measured, it is 1 upon full scale deflection of the current, 1 upon IFS. Okay, so it is ohm per volt. Clear? Now, as far as the final equation is concerned, we will come over here that how it has come. But as far as the magnetic torque experienced by the pointer is concerned, that is the deflection of the meter, that is theta m, is proportional to the E is something is the RMS value of the source voltage, you can say. I is the RMS value of the source current, and cos theta is the power factor, real power factor. So it is Ei cos theta. So if I will remove the proportionality constant, so here I am assuming that the instrument proportionality constant is going to replace by the Em. Clear? So now what will happen? How you are going to operate these kind of instruments? You can be noted that as far as the operation is concerned, operation of these kind of instruments are concerned. Okay, you have been noticed that the field that is the pointer or the which is mounted over the spindle. Okay, can be uh, move forward and can bring back in the reverse direction, that means towards zero simultaneously. Okay, by varying the direction of the current passing through the coil. Okay, through the movable coil. So that means by passing the direction of current. Okay, as far as the DC is concerned, it is fixed because in that case the polarity will be fixed. But as far as the AC current is measurement is concerned, by changing the direction of the current, so because when it will change the direction of current, direction of the flux is also changing, induced flux is also changes. So therefore the torque which is mounted over that particular pointer will be moved either in the forward direction, that means in the increasing value, that is the positive value, or the decreasing value, that is the negative half of the cycle. Okay, so by this by applying a movable coil within the two fixed coil, okay, that is called the field coil also sometimes connected in series, you can manage the movement of the pointer by applying the torque in a particular direction, that is either in the forward direction or in the reverse direction. You must also be it must also be noted that as far as the control torque is concerned, so these control torque are provided by the two springs, okay, over which using which that particular pointer is mounted over it. Okay. Now, as far as we talk about the damping is concerned, so damping as in case of PMMC, you might have noticed that the damping is provided with the help of by applying the eddy current, because that is the natural phenomena is some there. And in case of the moving iron type of instrument, it is created using the air friction damping, because the movable part is so sensitive that it could have been damaged. You cannot create eddy current damping in that case, where the eddy current is naturally originated, is influenced as far as the PMMC measurement is concerned. So in the similar fashion, the air friction damping is also used as far as the damping torque is concerned, or the deflection torque is concerned, in case of the electrodynamometer type of instruments as well. Okay, so it is a common thing as far as the damping is concerned, or damping mechanism is concerned, between the moving iron type of instruments and the electrodynamometer type of instruments. On the other hand, as far as the eddy current damping is concerned, which cannot be used in these kind of instruments, that means as far as the moving iron instrument and the electrodynamometer type of instruments is concerned, because the reason is that the field, or in other words the fixed coil, okay, the both the fixed, whenever I say the field, so you note it down that it is the fixed coil. So the two fixed coils are very weak, okay, on account of the core of the coil is concerned, because normally these coils are basically air cooled coil. Okay, or in other words, you can say that the inductor is a linear device. Whenever you are considering inductor as a linear device, so these things we have been already discussed in a very conceptual way under the head of the network theory. Okay, so you were assuming that the core of the coil is the air core, so that's why the field is very big, because if it is a ferrite core, obviously the inductance is very high. Okay, So in such a case, the permanent magnet it will be requiring, okay, you required of some kind of permanent magnet mechanism for generating the eddy current and thereby the eddy current damping. So this is not possible in case of the electrodynamometer type of instrument, and that is the reason, okay, that and even if you can manage that, in that case what happened, it will distort the operating magnetic field of the instrument. Okay. So there is the restriction that why you should not generate, why you cannot generate the eddy current damping. So obviously in that case, which is the best option as far as the damping mechanism is concerned, other than the air friction damping and the hydraulics one. So obviously in that case, we are bound to go for the air friction damping. Yeah. What is the range? It can measure nearly around 0.005 to 0.006 webers per meter. Okay. uh, Shielding is required. The question comes that do you require a kind of shielding, that means the protective mechanism, protective shield to protect the actual circuitry part of the electrical elements involved in the electrodynamometer design? Answer is yes, because the field produced by the fixed coil is somewhat very big, so it can easily influenced by the external world. So that's why a shielding mechanism is required. Even in case of the DC measurement, the earth magnetic field even may affect it, remember, okay, because theoretically again it can measure both, but obviously it is the one of the best solution as far as the AC measurement is concerned if you will compare these three solutions. Okay, that's therefore it is necessary to shield an electrodynamometer type of instruments to protect it from any kind of possible effect of the stray magnetic fields, that means near surrounding magnetic field. Okay, air cooled electrodynamometer type of instruments are also protected against the external magnetic field by enclosing a casing. Okay, and what kind of casing you are going to use? Obviously the permeability of that kind of casing, that means the material which you are going to use to create a casing should have a very high permeability alloy. Okay, because in that case the external magnetic field will be influenced only the casing part because it is a high permeability, and the device or instrument which is kept inside the casing will remain unaffected from the external magnetic field, or it can minimize the influence of the external magnetic field. Okay, normally as far as these instruments are concerned, it comes with the 100, 120, 150 divisions, which is a very normal scenario. Okay, now let's see mathematically that whether we can be justify that if electrodynamometer is a transfer type of instrument, in that case the performance of, why we say that it is a transfer type of instrument, because uh, we claim that the electrodynamometer or electrodynamic type of instruments will give you the equal kind of performance as far as the low frequency signal is concerned, or in other words direct in an ideal DC signal is concerned, and also when you will apply a AC supply. Okay, so as far as the AC measurement is concerned. Okay, so let's see mathematically can we justify it or not. So for our understanding, here we are consider that I1 is the instantaneous value of the current which is passing through the fixed coil. Remember, I have already show you the arrangements that as far as your arrangements are concerned, you might have seen that an entire circuit is in series connection. Okay, that is in sequence. But for our better understanding, let us assume that amount of current which is passing through the fixed coil is the I1, and amount of current which is passing through the movable coil is actually I2. In that case, the fixed coil is designated by L1 and the movable coil are designated by the L2. Obviously, when more than one coil exists there and the current is passing in this series, so obviously there will be a mutual inductance, right? So in that case, there is a certain amount of flux linkage will be generated by a coil, where you will get the total amount of flux linkage is more than the self inductance generated by a particular coil. So let's say I am assuming that phi 1 is equal to L1 I1 plus M I2, and the flux linkage over the coil is not F, it is basically it should be the OF, correct. Over the coil 2 is actually L2 I2 plus M I1. I hope that this should be clear. So therefore, what is the total amount of electrical energy input you have given to the this particular circuit? That is the sum of the two. So for the fixed, due to the fixed coil, it is E1 I1 dt, and due to the movable coil, that is over which the pointer is mounted. Let us assume that is E2 I2 dt. Yeah. So in that case, if it is so this is, remember, total amount of input energy you have given. Let us calculate what is the amount of work done also, and using the principle of conservation of energy, we can also see, okay, what will the total amount of electrical input energy, how it is being used. Certain amount of energy will be passed through due to the change in energy stored and the mechanical work done. What is the mechanical work done? When due to the experienced torque, when the pointer moving in forward or in reverse direction, that is the amount of mechanical work done. Clear? So from this particular statement, you know the value of E1 and E2 in terms of L1, I1, and that means the flux linkage. So if you will substitute these values, you will get these standard equations. Okay. So here I give you the assignment question, that derive the torque equation and try to find out, apply the steady state condition, and try to find out the uh, torque experience by a electrodynamometer of instruments is concerned at the steady state condition. Clear? So that is the assignment for you. So ultimately you have to remember, should not skip these intermediate lines. Okay, you have to ultimately substitute these values and expand it correctly. Okay, and then you will get this statement. Now, energy, what is the amount of energy stored in the magnetic field? It is half I square L. So how many fields are here? Two fields and a mutual inductance. So it is half I1 square L1 plus half I2 square L2 plus I1 I2 M. So therefore, if it is stored amount of energy, what is the change in stored amount of energy? D by dt of that value. So when you will take the derivative of that particular value, obviously you will get the another expression that is shows the change in energy stored. Okay, change in amount of energy stored into the coil. So once you got the change in energy, amount of energy stored, okay, and you also know the amount of the mechanical energy you want to calculate, the total amount of electrical input energy is already given over this treatment. Change of energy stored is already known. Okay, and you know that the total electrical input energy is equal to change in stored energy plus mechanical energy. So I hope that from here you can calculate the mechanical energy, which is the difference between the total amount of input electrical energy minus change in stored amount of energy. So you do this homework and finally you will get this equation. Okay, that is the mechanical energy what you have got. Clear? Now in that case, now if you will assume that because of the self-inductance, we have been says that if you will take both the values are equal L. So if L is a constant, in that case DL will be 0, change in inductance will be 0. Substitute that statement also. So ultimately what you will get, the amount of work done, that is Ti into d theta, Td theta, right? So in case here I am assuming that Ti d theta is equal to I1 I2 into Dm, because this DL1 and DL2 will be tending to 0. Or in other words, the amount of torque is, that is I1 I2 into dm by d theta. Okay, now if the amount of current is exactly same, so what you will get, Ti is equal to I square dm by d theta. So you see that amount of torque experienced by the pointer is proportional to, okay, root mean square of the current. Okay, so that's why it can measure the true RMS value of the current. Yeah. Now, what can be the possible errors? As we said that the frequency error is obviously can be there. External magnetic field can influence. Temperature can be a factor because there is a inductance, and as far as the real inductances are concerned, it also had a certain amount of resistances also, and due to the resistance, the temperature effect can be a matter. Other than that, eddy current error can also be there. What is the biggest advantage? Because as a true transfer type of instrument, it can measure the RMS value of the voltage and current very, very accurately, far more accurately as compared to the moving iron type of instruments. Yeah. Certain disadvantages, it has a low torque to weight ratio. If it is a low torque to weight ratio, then what will be the disadvantage? Whenever the pointer will move, it will get the friction error. Okay, because the friction is increasing. Okay, if torque to weight ratio is very high, then the friction is less. Remember it. Okay, so that is one of the reason. Then number two, these kind of instruments, as far as the electrodynamometer type of instruments are concerned, they are quite expensive as compared to the PMMC instruments or even the moving iron type of instruments. So cost is a factor. You have to manage with it. Otherwise, as far as the AC measurement is concerned, it will give you very accurate result. Okay, the instruments are sensitive to the overloads, and the mechanical impact can be also there. Okay, the operating range is certain between 0.1 to 0.5 weber per meter. Okay, as compared to the PMMC instruments. I mean, in PMMC instrument, the range is 0.1 to 0.5 weber, whereas in case of the electrodynamometer type of instrument, it is something around 0.005 to 0.006 weber per meter. Okay, very low, very low. Okay, so that means it can entertain only very weak magnetic field, or in other words, you can say that even a very weak magnetic field can affect the performance of the device. Okay, very weak magnetic field, even in fact you can say around 100 times weaker also. Clear? Okay. So scale is uniform or non-uniform? Obviously, the scale is non-uniform, but you can convert into the uniform, because once you got the reading, because reading you are always getting in terms of I is the RMS value of the current, and you are getting the torque is proportional to I square. So once you got those values I square, that means square value. So you prepare a lookup table, and using that lookup table, we can calibrate the pointer. And once that particular calibration is done, then the same scale of the pointer will can give you a uniform reading. Okay, so there is a technique. So whenever you will visit to the lab, next time you ask your lab assistant to help you to get understand these things. Okay, how a non-uniform scale is being calibrated and can give you a linear response. Fine. So these snapshots I have taken from one of the reference books. So you can either refer your one of your reference books I have been already listed, or you can directly refer these materials. Okay. So now finally we wanted to see that whether it can really perform as a transfer instruments or not. So to satisfy that, what we are going to do, we are going to see that how the electrodynamometer type of instruments can perform as far as the AC supply is concerned, how it can operate as far as the AC supply is concerned, and how the same instrument can affect can operate as far as the DC supply is concerned, or the sinusoidal supply is concerned. Okay, remember our source is the sinusoidal in nature, which is one kind of AC signal. Clear? So I will take the same assumption because of the DC. Now to have more clarity, remember small I and a small I1 and I2 have taken as a instantaneous value of the current, that is the input AC signal, and for the DC I am considering the capital I1 and capital I2. Okay, but again the subscript will be same amount of current passing through the fixed coil is I1, and amount of current passing through the moving coil is I2. If it is so, deflection torque, that input torque or the deflection torque, how much it will be? It will be I1 I2 dm by d theta. We have occupied from this statement, right? So from examination point of view, I would advise that don't write it here. If you are asked, you straight away derive the entire expression, and then you reach that Td is equal to I1 I2 into dm by upon d theta. Okay. Now, when you will apply the control torque using the air friction, in that case, how much it will be? It should be proportional to theta. So let us assume that is Tc, and Tc is equal to K into theta. So therefore, your theta is proportional to is equal to I1 I2 upon K dm by d theta. Now, for the small change in mutual inductance, you will get a incremental change in theta. So therefore dm by d theta is a very small factor, k is a constant, so ultimately theta is proportional to I1 into I2. And if you know that, because both the coils are connected in series as far as the measurement of current is concerned, now there is a question whether you want to measure the current or whether you want to measure the voltage. There are two same amount of fixed coil, and there is a moving coil, right, in which is fixed in which is fitted between the two fixed coil. Now if you want to measure the current, so what combination you got to do, you have to connect all these coils in series. So if it is in series, so I1 is equal to I2. So in other words, deflection pointer theta is proportional to I square. So for any DC supply, the deflection is proportional to the square of the current, and hence the scale is non-uniform, is a crowded at the end, but it can offer the measurement of theta. That means the pointer can measure, okay, the flow of current, the magnitude of current in proportional to square of the value, in proportion to square of the value. Now let's see the how it operates as far as the AC signal is concerned. So for AC signal, as I have told you earlier, that I am assuming that it is a small I1 and a small I2 through the fixed coil and the moving coil respectively. In that case, the input torque is equal to I1 I2 dm by d theta. Okay, and again, if I wanted to measure the current, I will try to connect both the coils, combination of coil, that is the fixed coils and the moving coil in series. In that case, I1 is equal to I2, and in that case, Ti is proportional to I square dm by d theta. This is not I2. Remember, in this equation, there is a mistake, printing mistake, you can say. It is not I subscript 2, it should be in this equation, in the second, where it is mentioned instantaneous torque of the pointer on the pointer is Ti is equal to I square dm by d theta. So I have mentioned in red color, correct it. Okay, if you will go through that kind of book. So, for a AC supply, the instantaneous torque is proportional to the square of the instantaneous value of the current. Now, remember, because it is a I square, so I square will always give a positive value, whether it is an increasing value or decreasing value. So, therefore, current varies and then the instantaneous torque is also varying. But as far as the moving system is concerned, due to the inertia, because remember, theta is varying with respect to the proportion of square of the I. So the inertia cannot follow such a rapid way. Okay, the inertia, that means what is the inertia? Whenever a physical body or mechanical body is experiencing a torque, okay, so it has the force or in a torque, you can say it has an inertia. Okay, so inertia cannot change so rapidly as the current is changing. That is what wanted to say, and that is the reason you cannot measure the instantaneous torque variation in the instantaneous torque. What you can measure, the average of the variation in the torque. I repeat, because the inertia has a limitation. The current, as the current signal can change so very rapidly, mechanical change or the physical change cannot be so rapidly. So the inertia experienced by the pointer doesn't allow it to change rapidly with respect to the change in current, and therefore you cannot measure the instantaneous value of the torque. What you can measure, within the duration of time, within the fixed duration of time, you can measure the average amount of torque, change in torque. So therefore, whenever you are going to measure the deflection torque, as far as the operating with AC signal is concerned, you are supposed to measure, as far as the electrodynamometer instrument is concerned, you are measuring for a fixed time period or for a complete cycle. So therefore, now TD, modified TD, you can say it is 1 upon T, 0 to T, Ti dt. Now Ti is I1 I2 dm by d theta or I square dt, and because dm by d theta is constant. Okay. Now let us say the same whenever the pointer is going to experience a steady state condition, it can only occur whenever the control torque is equal to the deflection torque. If you will compare both the statement, your theta is how much you are getting. It is 1 upon k, which is a constant. Dm by d theta is another constant. 1 by t is a constant. So integration of 0 to t I square dt. So therefore, the deflection experienced by the pointer, okay, is a function of the mean. Is a function of the mean, because it is 1 by t will give you a mean of the square of the current. Okay, so if the pointer scale is calibrated, if the pointer scale, be noted very carefully, if the pointer scale is calibrated, that means the pointer scale indicator is, okay, not indicator, the pointer scale is calibrated in terms of the square root of this value, that is the square root of the mean of the square of the current values. Okay, in then the RMS value of the AC quantity can be measured directly by this particular mechanism. Here you got the answer what I have been asked you a few minutes back, that whenever you will able to visit the lab, ask your lab assistant to help you to understand this experimentation. Okay. Now let's say we consider the um, uh, office like supply or the AC supply, because our AC supply is sinusoidal in nature. So if it is so, I am considering that I1 is equal to Im1 sine omega t, and I2 is by some delayed signal Im2 sine omega t minus phi or minus because theta you have considered for the indication of the deflection. So I am considering it phi or xi, something you take. Okay, so in that case, how much average deflection torque you will get? Dm by d theta upon into 1 by t integration of 0 to t I1 I2 dt. Substitute the value of I1 I2. Okay, solve it. So how much you are getting? You are getting I1 I2 cos phi dm by d theta, because im1 and im2 are the ultimately constant. Okay, so I1 I2 are the RMS value of the current, remember. Okay, im I2 are the RMS value of the current. I1 is equal to im1 upon root over 2, and I2 is equal to again im2, which is RMS value of the current upon root 2. So I1 I2 d d theta. So now what is as ultimately theta you are getting by applying the steady state condition or the equilibrium condition when the pointer will experience a steady state condition. In that case, I1 I2 cos phi dm by d theta is equal to k theta, or in other words, theta is equal to I1 I2 upon k cos phi dm by d theta. Remember, this k cos phi is added additionally. That is the reason that we can measure the active power factor, in other words, the power factor of the signal, also with the help of the same electrodynamometer of instrument. Though these things we will discuss in detail in the next unit. Yeah, so it has been clearly shown that as far as this instrument is concerned, if you are going to apply a sinusoidal current, so it can measure, the pointer can calibrate it in terms of the square root of this value, or in other words, you can take the square root of the mean of the square of the current value. In other words, RMS value of the AC quantity that can be directly measured by the help of these kind of instrument. So you see the performance of the DC signal, you see the performance of the AC signal. So it clearly shows that how, why it can be considered as a transfer type of instruments. Now, for a couple of minutes, we will see that how the electrodynamometer type of instruments can be used for the purpose of measurement of a current signal and for the voltage signal. So, in other words, whenever you wanted to use it as a ammeter or as a voltmeter. So, I would advise you that you go through the lecture notes. I have been already provided you the PDF file, and you see between these, compare, try to compare with these two circuits, like for example figure number 2.17 where it is mentioned electrodynamometer ammeter, and you go through the circuit figure number 2.18 where it is mentioned electrodynamometer voltmeter. Clear? And try to notice the difference between these two circuitry whenever you are going to use the same electrodynamometer instrument for the purpose of measurement of current and voltage. Okay, spare a minute of time and then you come back with with your analysis, or I will answer. Have you noticed the difference? If you compare these two characteristics, have you noticed the difference? Okay, the difference is if you see the electrodynamometer type of emitter, that means device as a emitter. So what you see that the additional in a real life scenario you have applied, because remember these two fixed coil and this moving coil are connected in series, है ना? Is series. Now across this particular moving coil, across, remember, across this moving coil you have applied a shunt circuit. Clear? Or a combination of a reactance resistance ratio, okay, in parallel to this. Why you wanted to do this? Because so that the frequency where this moving coil is operating, at the same frequency this parallel circuit reactance resistance circuit can also be matched, and once it matched the supply of that particular frequency, in that particular case, at that specific frequency, because remember, if the frequency is going to change, you are talking about the measurement of the AC signal. Okay, so if the frequency is going to change, then the performance of the measurement will definitely affect it. So to get the exact measurement, what you do, that you have done this kind of arrangement, the shunt reactance resistance type of arrangement, and you try to match the frequency of this reactance resistance coil equal to the moving coil, so that you can measure the exact RMS value. Okay, similarly if you see the voltmeter here, and remember load resistance is connected somewhere here where you have applied the E, your supply voltage or electromotive force. In case of the voltmeter, what will happen, this circuit is connected using a resistance only, unlike the reactance resistance circuit. But remember, whenever you wanted to use it as a voltmeter, this resistance R what you see here, or RB sometimes it is mentioned, it should be a non-inductive resistance. One given non-inductive resistance, that means as well as a pure resistance. So non-inductive type of resistance which has a least amount of influence of the temperature, because resistance is the influence of the temperature. So you require a special material, a kind of resistor which is a low inductance in nature and also less influence with the temperature variation, so that you can get the accurate result. Okay, I would say that you try to do this homework over this particular aspect, and in the next lecture for the few minutes we will discuss this particular aspect. Okay, so that is how you have done the electrodynamometer voltmeter arrangement. That means whenever you wanted to use electrodynamometer as a voltmeter. So whenever you want, now if your purpose is to measure the wattmeter, this application we will discuss in detail in the next lecture. What you need? Current coil and the potential coil. So remember, the two fixed coils are used here to give you the total response of the inductance of the current coil, and the moving coil is used here as a pressure coil or the voltage coil which is applied in shunt. Okay, this is all the things I am telling you, but rest of the things I will discuss these things in detail as far as the next unit is concerned. Okay, that how you can properly use it as a wattmeter method. Yeah, this is what you have seen. I'm trying to show you that RV. Okay, so it's a low, you can say that temperature influence, and the very high low non-inductive type of resistance. Okay. So here in this demonstration, terminologies are a bit different. IF and IM is given, but it will give you ultimately the same result. How can you measure the actually power? So these things, as far as the wattmeter application is concerned, we will discuss in detail in the next time. Clear? So with this, I am stopping the